Dr. Joan Vernikos earned her PhD in pharmacology at the University of London. She was recruited by NASA in 1964 to study stress and keep astronauts healthy, and she appointed NASA's Director of Life Sciences. Dr. Vernikos, you may start your presentation.
In life, things happen. It is good to make plans, but what finally makes the difference depends on how you choose to use them. My father left the island of Sifnos in 1895 on a boat to France to study medicine in Montpellier. He knew no French. After he graduated, he specialized in infectious diseases. He was in Paris. He even had a lecture from Pasteur, or so he told us. With his credentials in hand, he headed for Alexandria to practice his specialty. Since he had no sons, he wanted us, his two daughters, to become doctors. My sister became a pediatrician, but only because my mother would not tolerate her having to examine adult male patients on her own. I too began in medicine, but soon switched to pharmacy when every day I had to walk through the anatomy room, so I chickened out. I therefore expected to spend my life working in a pharmacy, but that was not to be. Political changes in Egypt, family planning to move to Greece, my bachelor's in pharmacy not acceptable in most places. It was very different times and very difficult. So I left Egypt to go to the London University, trying to get some more acceptable degree. I went to the School of Pharmacy and maybe a master's or some more recognizable qualification. I was fascinated by one of my professors who worked on stress and hormones. He was moving to the Royal Free Hospital School of Medicine, and he asked me to join his research lab to work on my master's degree. By pure chance, the new chair, professor of pharmacology, was one stunning Greek redhead, Nora Zaimis, and some of you may have heard of her. She was famous for synthesizing the methonium compounds, hexamethonium, a ganglionic blocker, and the first drug known to lower blood pressure, and the longer chain decamethonium, a neuromuscular blocker, and the first muscle relaxant used in surgery to reduce the size of surgical incisions. After a few months, my research was going well, and I was advised to bypass the master's degree and switch to the PhD program right away. It was the exciting time of working on prednisone and prednisolone, the new synthetic steroids. While in London, I married a Greek student who needed someone to support him through a PhD at Ohio State University. So off to America. I found myself teaching pharmacology to medical students while continuing my research on stress. In 1964, the chair in physiology at Ohio State was invited to organize NASA's first life sciences research unit in California. He asked me to join him. After all, he said, if you put a man on top of a rocket, it must be stressful. My colleagues thought I was crazy to go to this unknown entity called NASA. But my choices were either NASA or back to a pharmacy in Greece. I made the right choice. By 1965, I was measuring stress hormones in astronauts Frank Borman and Jim Lovell during their 14-day space trip on Gemini 7. Were their corticosteroids going to be as high as everyone had expected? Actually, not. They were even lower than when they were walking around Earth. Was space not stressful? Or was gravity the stress we have on Earth? Or were these first astronauts a different breed? after flying dangerous missions over Korea, space was fun for them. Later, the younger recruits with no military experience showed plenty of stress. But at that time, it seemed like the end of my beautiful career. The lesson I learned quickly was that things are not always as you expect. No one knew what the effects of space were on the human physiology. As you've probably heard in the last few days, space provides many factors that could affect the human body. For instance, the environment in and outside the capsule, carbon dioxide levels from the life support system, which, though safe for one day, accumulate in the body over time. Toxicity from the iodine used for years to sterilize the water, until in a ground study one day it turned out to be toxic. Then it was replaced by silver nitrate that the Russians had been using. Maybe they still use it. The absence of 24-hour day-night cycles replaced by 90-minute cycles in space, and inadequate proper light intensity that affects circadian rhythms, as well as vitamin D blood levels. Taking a pill in the morning in space is not quite the same as on Earth. Interference of normal drug dosing and drug effects by shift work, EVA, extravehicular activity, workload, exercise, diet, and the participation of astronauts as test subjects are all confounding factors and difficult in monitoring and for controlling the studies. Being away from Earth and other humans has emotional consequences. The early, reduced, and prompt and sustained reduction in plasma volume by as much as 10 to 20% must affect drug doses and may increase the risk of kidney stone formation as well. Sleep is a major problem in space. I had studied the 9 astronauts in 3 Skylab missions in the early 1970s. To help them sleep, they had tried all 4 drugs in the medical kit, including the old-fashioned chloral hydrate. Nothing worked. To this day, with more modern sleeping medications like melatonin, having problems sleeping, as well as the quality of sleep, are still a major source of discomfort in space. But let me tell you a story. My husband and I were having lunch one day in Paris with Russian cardiologist Oleg Atkov. He was one of the first to spend 6 months on the Russian Salyut spacecraft in 1984. Asked what the worst part of being in space was, Atkov thought for a while and replied, having no sensation of putting your head down on the pillow. I had never thought about it that way, but it made a lot of sense to me. Nobody sleeps well sitting up in an airplane or standing up, which I remember trying to do as a student on a train from London to Greece. It was assumed that inactivity was the fundamental cause of the effects of spaceflight, so countermeasures focused entirely on exercise. Living in space is unlike any other extreme environment, like altitude, for instance, or heat or cold, where the human eventually may adapt. After 1 year in space, humans to date have not adapted in spite of intense exercise countermeasures. And you may think, why should they? You may feel a little better while exercising, but the minute you stop, you're instantly back in microgravity, responding to it like it's the first time. Unlike on Earth, where the post-exercise response is a significant factor for about an hour at least in the benefits of exercise, there should be no such post-exercise response in space. But as far as I know, no one has tested this either. During my bed rest studies, it was evident that the physiological changes I saw were similar to those of elderly people. not because they are exposed to less gravity, but because they use it less. I called it the gravity deprivation syndrome, where space, bed rest, uninterrupted sitting, or aging are all exposed to or using gravity less. It is possible that over time, epigenetic changes may result in more permanent changes. On the other hand, gerontological pharmacology is now a significant field and should be used as a reference for anticipated changes in drug responsiveness in space. So let's get back to basics. As the Earth rotates about itself and around the sun, we have day and we have night. At night, we lie down to sleep. And when the sun rises, we get up and we move about. Gravity, of course, at 10 to the minus 5 in Earth orbit, is way below threshold for optimal human physiological function. We now have a better idea of what is our physiological GZ threshold. The artificial gravity dose response studies of Dr. Papadelli have come closer to establishing this threshold for physical loading on Earth. We were born, developed, and evolved in Earth's gravity. Standing up, we call it 1 GZ, pulling downwards to the center of the Earth, providing our load. On the moon's 1/6 GZ on its surface, astronauts were upright, but could not walk normally, and you could see them hopping. On the Mars surface, about 1/3 GZ, it should be at or above the GZ physiological threshold. This might suggest they should be able to stand and walk on Mars, though their head would probably be above the Mars atmosphere. We have learned much about the role of gravity on human physiology, both living in space and aging, which are all generally wasting conditions. Ground simulation of living in microgravity by head-down bed rest has been a useful model in understanding space physiology, particularly with respect to reducing the GZ directional factor and load. Systematic pharmacological studies would be useful not only for astronauts, but for the geriatric population as well. Nor, as far as I know, has the gerontological drug and toxicology experience been used as a source to space pharmacy. But there is more to gravity than GZ. We no longer have in space our daily frequent change in posture. You cannot stand up in space. Intermittent GZ, as in postural change, every time we stand up, seems preferential for muscle and metabolic responsiveness. What are the frequency requirements of the GZ stimulus for maintaining sensory thresholds? Better studies have indicated that repeated GZ intermittent stimulation every 30 minutes to 2 hours during the awake hours may be optimal for sustaining sensory responsiveness, especially needed for balance. What about G sub X? Do you know what G sub X is? That is the direction gravity would pull when you're lying down and is pulling across your chest, not along your height. Might G sub X during hours of darkness be required for optimal sleep? Possibly with vitamin D, magnesium, and other maintenance supplementation, which may also be required. Should circadian rhythm synchronization be revisited with stronger zeitgebers to maintain day-night cycle cues? As we know, after 1 year in space, humans have not adapted. Recovery and rehabilitation has taken several years. Is adaptation to living without gravity possible at all? During my bed rest studies, it was evident that the physiological changes were similar to those of elderly people. The field of gerontological pharmacology is now significant and should be used as a reference for anticipated changes in drug responsiveness in space. Absorption is slower or inhibited in both conditions. Space motion sickness medications do not work by mouth, but as Jim Bajan had shown, work by injection or by intradermal absorption. That's when intradermal drug administration was developed for us. For instance, the combination of scopolamine and dextroamphetamine has been useful for nausea in liftoff and landing. Nutritional and pharmacological supplements probably need higher doses rather than traditional earth doses. Systematic pharmacodynamic and pharmacokinetic studies have been done early during a mission when dynamic changes are greatest. They've only been done on day 2 and 3. The reduction in plasma volume probably has not completely stabilized. Apart from pharmacology, absorption and elimination of drugs has not been studied systematically. And certainly no dose-response studies have been done. So far, when it comes to choosing a dose and route of administration, Earth standards are used. As Lambertson said of the space program in 1965, the purpose of using drugs in space is to maximize capabilities and minimize hazards. So if you were wondering what next, there is no shortage of questions to be answered. We are all lucky to be here at this meeting, as I did, new things and new ways of looking at what you knew. We are still at the observational stage. We are living in exciting times of discovery, not only to go because we can. It is crucial to make space travel safe and possible, at least for short periods for most of us. With that, to expand awareness of the changing physical environment to help us better understand life, health, and aging here on Earth. Thank you very much for giving me the opportunity to come and talk to you today and to join you in this wonderful meeting.